What an integral veteran you're becoming. We're still on integration by parts, and I'm going to show you this very dangerous and enticing technique called tabular integration. Before we get there, let me remind you where we are. We're still in integration by parts, but now we're learning this little tabular trick. And anytime you're working on integration, you should honor this statement because it's a universal truth. All right, enough with the ominous stuff. Let's get to this tricky thing called tabular integration. And if you've been cruising along in the notes, these are also in the notes. And I'm going to use the two problems that we've used so far, or two of the problems we've used so far. This is the very first question you used to learn integration by parts, and it went smoothly. This was another question, and this is one where you ended up having to do integration by parts not one round, but 2 rounds. Well, both of these problems could have been done by tabular integration, and for that reason, you're going to say, hey, why the heck didn't you show me this in the beginning? Well, there's a good reason for that. So for tabular integration, we're going to set up a table, and just like regular integration by parts, we're going to select a U and a DV to be installed into this table. So my thinking's the same. Pick out something from here for you that is easy to have a derivative of. So X seems to fit the bill. Pick out something that's reasonable to have an antiderivative of. Cosine of X seems to fit the bill. And then you have this third column, plus minus. Let's just, for right now, say always begin with a plus, because wouldn't you want to start every endeavor with a positive attitude? Who would want to start off with a negative attitude? All right, so we have this filled, and you might be saying, well, why wouldn't you have put a cosine of x here? Because I can find the derivative of cosine x really easily, and then put an x here, because I can find the derivative of x very easily. Well, the reason for that is for tabular integration to work, this column, as I go down and take its derivative, has to eventually end up with a derivative value of 0. Let's just watch and see. The derivative of u would be 1. The derivative of 1 would be a 0. I know I've made a good selection. All right, so now over here, I need to do the antiderivative. And what's the antiderivative of cosine? It's sine. What's the antiderivative of sine? You would say, well, that's cosine, but it's really not. It's negative cosine of x. Okay. I could continue, but why do it? Because I've already stopped in this column. This column just alternates. Plus, minus, plus, always start off plus. Once you've done that, and you should be pretty meticulous about that, you need to kind of look down the diagonals. If I look down that diagonal, I'm going to string together those 3 terms. Then I look down this next diagonal, and I say, wait a second, I'm missing something. Well, alternating plus, minus, minus. All right, so I was able to complete 2 full diagonals, and when I do that, what I'm really saying is this integral could have been found by this magic thing. I simply take this term, x times sine of x times a positive, which is x sine of x, then 1 times negative cosine of x times a negative 1 is positive cosine of x plus c. This is the exact same answer we would have gotten for that had we have done integration by parts. Notice I remembered the plus c. So this tabular integration is a way around doing the integration by parts formula. I know what you're thinking. You're thinking, why didn't he tell us about this earlier? Well, before I do this, before I tell you why, let's do this problem. I'm going to do it faster. This is one where we ended up having to do 2 revolutions or 2 cycles of integration by parts. So same thinking. Give me something here that's easy to take a derivative of. But wait, not only do I have to have something that's easy to take a derivative of, it's a deal breaker if it doesn't eventually have a derivative of 0, like I had there. If I never get down to a derivative of 0, I never get to stop this process, and nobody has time to donate the rest of their life to something like this. So the derivative of x squared is 2x, the derivative of 2x is 2, the derivative of 2 is 0. That tells me I've made a good choice. If I chose that for you, that has to be my dv. That's cosine of x. Remember, I have to be doing antiderivatives now. Let's see. Remember, your brain can really play tricks with you on antiderivatives. In fact, what I would probably do is check it. The derivative of negative sine is negative cosine. The derivative of negative cosine is sine. The derivative of sine is cosine. That seems good, unless my brain's playing tricks on me. I go ahead and do this alternating. I go one more because you're always going to end up having to do that. And then I just take a look. As long as you're pretty neat and organized, this diagonal will form one term, this diagonal will form another, and this diagonal will form another. And so when I say equals, that integral is equal to, I probably need to write small here, this times positive 1. This times negative 1 would end up being a positive. This times positive 1. By using this tabular integration trick, I avoided having to do the integration by parts 2 rounds in a row. Now is the reason why I didn't teach this as the primary method. This method is only going to work if you can find something where the derivative eventually leads to a 0. So if I look at this one, I'd say, okay, well, I should go with x to the third plus 5. Because if I do that, I would then have a 3x squared, a 6x, a 6, and a 0. And it seems like I did an awesome job. Tabular integration, here I come. However, that means here I need to have the natural log of x. And then that means I need to find an antiderivative. I can't find an antiderivative of natural log of x. Spoiler alert, someday we'll be able to. But right now I can't find the antiderivative of natural log of x, and even if I learn a way to do it, it's going to be difficult, I guarantee you that. So if I can't do the antiderivative of natural log of x, I say, okay, scratch that. I'll put the natural log of x over here, and the x to the third plus 5 over here, because I could do the antiderivative of x to the third plus 5, and I could do the derivative of natural log of x. It's 1 over x, or x to the negative 1. So that seems like life is going well. I can just continue on with this, But the problem is, as I continue on with this derivative, it will never eventually equal a 0 like it did over here, which means these columns will never end, and I don't have time for that. So tabular integration is only going to work if you can find an appropriate thing for here, and this piece eventually has a derivative of 0. In this case, it doesn't, so you could not do tabular integration. I highly recommend that you check out this problem in our notes. We're continuing on in our notes. That's problem number 6. And this one does integration by parts. And then if you look down below, it says another number 6. I'm not sure why I did that, but remember this is all in your notes. There's the integral of inverse sine of x dx. And normally you'd say, I can't do that. Well, you might be expected to do that. So this problem runs you through that, and it shows you that when you get to this part where you're doing regular old integration, relying on any technique you know, Sometimes it's integration by hand, most of the time. Sometimes it's integration by parts for a second round. In this case, you ended up having to do U substitution in there. Would the AP test writers ever do that to you? They might. This ends your education in integration by parts. Remember, this is a true statement, and if you don't look through these notes and if you don't practice these homework problems, you might fall victim to that.